All right, so let's get started. Today we'll wrap up the discussion that I started in the previous lecture, and all of this is related to the fact that we are building our first model with the goal of predicting the zone temperature in a space. And we established that we are not really interested in modeling all of the HVAC equipment, but we sort of abstract its operation in just one single term, which is the heat flow in the forced air HVAC component. What we are interested in modeling is the system itself, the zone, and its physical boundary or the building envelope, and how the heat flows into and out of this building envelope. And to do so, I sort of gave you a refresher on the basic mechanics of heat transfer and the first principles of heat transfer, since this is the first principles based modeling. And we utilize that to essentially establish that if we have an isolated wall, and this was your entire system where you had a wall, where you had this slab or a wall, and this could be made up of many composite layers. So we represent the total thermal properties of all of that using a single resistor and using, in fact, two capacitors, and we went into Y2 and Y01. But essentially, the model we had was that we want to have a state which denotes the temperature of the outside surface of this slab or wall, a state to denote the inside surface, and then the outside temperature and the inside temperature of the air are kind of inputs to this model, right? They are not really states. So what we last discussed in the previous lecture was this very sort of visual relationship of how you can now use differential equations to sort of define or model the rate of change of these two temperatures that you sort of pulled from thin air and are modeling that this is how the heat will flow through this wall. Right, so it's very clear that we have convection on either side if this is a real building and there's air inside the room and outside the room as well. And then there's a conduction term which can be used to compute how fast this heat from the outer surface, which is usually much more warmer if we are talking about summer months. So that term appears here, right? So this is delta T by R. And then there's another term which I haven't highlighted specifically in color, but the outside surface of this slab, if this was like an external wall of a building, this will also get some direct heat flux from other surfaces which are outside the building and also from direct sunlight. And so that flux could be a quantity which is, say, Q source watts per meter square. So you would look at the cross section or the surface area of this wall and multiply the flux times the total surface area to get the heat input, which is directly getting added and is changing or influencing the temperature of the outside surface directly. And besides that, there was this notion of the thermal capacity. So this slab or this mass of material has some thermal inertia or some thermal mass, which appears here in this term of capacitance in this simple model. And so this model has a name. It's called the 3R2C model, and essentially, this is where we sort of stopped last time. So any questions on this, first of all? Because this is what we will use to build up an entire zone model. Okay. So now the next logical thing to do, I mean, if we are good with this sort of modeling of 3R2C, I now propose that in reality, this model is useful to describe the heat flow and dynamics of the external wall or a slab, but this is not really the model we are looking for, because we want to model zone dynamics or zone temperatures. Whereas in this model, the zone temperature T of Z is just a boundary condition to drive the dynamics of T2 and T1. That's what the role of this TZ term is in this equation. So if we had to extend this model, if this was a thought experiment and a hypothetical zone with only one wall, and then the zone is on the other side, how would we extend this model so that TZ is no longer a boundary condition, but it's also a state, okay? So one thing which is obvious is when it is a state, it needs its own storage element as well. So let me pose this question before I show you the answer. In a zone, so in the wall, the capacitance C denotes the thermal mass of the material of construction of the wall. But in a zone, where's that thermal mass coming from? What are some ideas? What would constitute as thermal mass for a zone? we need a thermal mass for a zone if we want to model that as a state, because if it's a state, it should have its energy storage element. So what could be the physical interpretation of the thermal mass of the air in the zone, or where is that coming from? What are some ideas? Yeah? So what entity in the zone is storing that energy? That's what a capacitor does, right? So air, right? So primarily, we are representing the state as Tz, not in this picture, but shortly. So the inertia element or the storage element or the capacitance or the thermal mass, they're all the same, which is associated with that state now is many things. It could be the thermal mass of this lecture or this desk over here, or my body and your bodies and the furniture and the chair. But for the most part, Tz is a measurement of the temperature of the air molecules. And so the total volume of the air in this zone also has some capacity or thermal mass. And that's what we will leverage to treat Tz as also a state. So it'll become clear with this picture. So I can first of all say that if I now look at the zone temperature node, so I'm focusing on just this part of the model, we've already established there's a convective heat transfer to the internal surface of this thought experiment wall. But another thing which we have previously discussed, not mathematically but sort of qualitatively, that the internal heat gain from occupants also changes the zone air temperature, right? When we looked at this convective heat gain, and I showed you these pictures. So there could be a heat gain arrow to zone temperature, just like there is a direct heat gain to the outside surface. It's sort of a similar mathematically. There is also a direct heat gain or heat extracted from the HVAC component, which we have lumped together into just one heat flow, right? So this heat flow is a combination of many things: the air handler unit, the VAV valve, and the flow rate and the supply temperature. So we are not concerned with all those intricate details, but this is obvious, right? So zone temperature gets influenced not only by the surfaces of the inside of the wall, but these direct heat gains. And then the air in the zone has some thermal mass. So if I know the volume of this zone by the geometry information of how the width, height, and depth of this zone is, then I can compute the volume of the air in the zone, and that has some associated thermal mass. So with this added insight, this same model of a single wall can now have an additional state, which is the zone temperature. So zone temperature is no longer just an input which drives the dynamics. It itself is getting influenced by a lot of other inputs. So you can now write another equation of the rate of change of the zone temperature, and that could look something like this. Okay, so this is of the same form as this equation, but now we are concerned with the rate of change of the zone temperature. And it's the same equation as always, that Q dot is equal to C times delta T. So C of the zone air times delta T, or the rate of change of the zone temperature, is this convective heat transfer term, which is coming from the interaction with this wall, plus these direct heat gains, which are a combination of the heat gain from the HVAC side and the heat gain from the occupants or the equipment in the building. All right, so now we can talk about this system as a whole, right? So we have a model that can give us the dynamics of how the temperature inside the zone would evolve. So if you look at this, the zone temperature actually just depends upon these direct heat gains, the previous zone temperature in some sense, and it depends upon T2. But T2 itself changes over time, and T2 depends upon the zone temperature and T1. And T1 itself changes over time, and it depends upon the temperature outside and T2 and some flux. So these are all sort of very closely coupled. So this is the model that we have ended up with, that we have a slab, and the inner surface of the slab we are treating as another state, which is the zone air. And these three first order ODEs can describe the dynamics of the states that we have introduced. And everything checks out that we have 3 capacitors and 3 states, or 3 energy units. So just so that it's explicitly clear which term is what, the states of this model or this set of ODEs are these three terms, T1, T2, and TZ, because they change with time and they are being described by these ODEs. That's what the state of a dynamical system was, if you recall. Then there's something called parameters. Or before we get to that, what are the inputs to this model, right? So a model has to have an input and an output. And I claim that the inputs to this model are these heat gains or boundary conditions which are driving the dynamics of these states. So the temperature outside appears where? It appears here. So that's the input term. This is not a state. Q source is an input. And then everything here is actually a state, T1, T2, TZ. But in this equation, we have two terms which are not state but inputs. So we just collectively say these four things in these three equations are inputs. And then what are these coefficients, C and CZ? These are all parameters, right? So the convection coefficient of air, the thermal resistance of the slab itself, the cross-section area of the wall, the thermal mass of the slab, and the thermal mass of the zone air, these are parameters of the models. These are neither inputs nor states. These are sort of fixed coefficients of the model. In fact, if you think about it, if I gave you a real wall and asked you to estimate or predict the temperature, you would need some values for these parameters. And we have seen previously how do you compute that based on each of these terms, the H, R, and C terms. They are a function of both the geometry and the property of the material that you are trying to estimate the coefficient for. Questions on this? This is the same thing, but we have sort of taken a leap to treat the zone temperature as its own state. And this is what the input-output view of this system is. Okay, so then what should we do next? Naturally, if we have three ODEs, what could be our next step? What do we do always when we get ODEs? I've been preaching this for 2 weeks now. We have to build a state space representation of this. So let's do that. So these were my state equations. I'm going to write this, and I claim this is the equivalent state space representation of that system, where you have x dot equals some matrix A times x itself plus some matrix B times u. And we can do our sanity check. Let's do it for maybe this equation first. So T1 dot depends upon T1 itself, and there should be a term which is negative HA divided by C, and there should be another term which is minus 1 by RC. So that's this term right here. T1 dot is this term times T1 itself. Plus there's a term 1 by RC times T2, which is coming from here. Oops. Did my thing just die? Probably. Okay, it's back. So we have a 1 by RC term which is getting multiplied by T2, which appears here. And then T1 also depends on the input Q source, and that multiplier would be 1 by C, and that appears here. Okay, 1 by C times Q source, and HA by C times T naught. So this first term, HA by C times T naught. So I don't have to convince that they are the same every time, but it's always good to do this sanity check by visually seeing that they are equivalent. The same applies to T2 and TZ. Right, so this is our state space dynamics. So it's again color coded so that you can associate what a state is, what A, B, C, and U are. There's no C here. So we ended up with a state space model now, where one of the states is actually what we are trying to predict, the zone temperature. So in fact, you can even treat this state as the output of this model. So let me ask you a question based on this state space form. What in this model varies with time and what does not vary with time? So you don't have to raise your hand. You can just yell out whatever you think is varying with time and what is not varying with time. The x variables vary with time. Very good. Anything else which varies with time? The u variables, okay. And what about A and B? Do they vary with time or not? Yeah, they're constant, right? So what you have really said is that x and u vary with time and the matrices have not, which is correct. And another way of saying it is that the states and inputs are time varying. Okay, so when I say x dot equals ax plus bu, I should really make it more explicit of what is a function of time and what is not. Right? So we have x dot, which is a function of time. The state is obviously changing with time. If the state wasn't changing with time, it's not an interesting system to analyze. It's a static system. It's not even dynamic. And then we have u of t, all these inputs. The temperature outside is going to change with time. The flux from the sun is going to change with time. Heat gain will depend upon occupants, whether the projector is on or off. HVAC operation is time varying. So that's good. So this is a dynamical system. Now my next question is this system LTI? And I'm not going to tell you, like I think I've already covered what LTI is. So I'm just looking for a yes or no. Is this system a LTI system? Can someone tell me what LTI stands for? Linear time invariant. So I'm asking, if you have forgotten, is this system a linear time invariant system? So who says yes, this is linear time invariant? Okay, and then the rest who doesn't think it's a linear time invariant would say no. So why not? You can only say yes or no, right? There's no middle ground. So who thinks this is not linear time invariant? Can I hear from someone who said this is linear time invariant on why they think that it is time invariant? So someone who raised their hand previously, what's the reason? Yeah, Aaron.
Because either A or B change with time.
Correct, right? So we had discussed this, and I spent some time when we went through this in a generalized electrical mechanical form, that the laws of nature don't really change with time. Okay, so we are assuming here that the resistances and the mass, the thermal mass of the wall, is not changing with time. This is an assumption. Why is this an assumption? I can give you an example where this assumption is not true. The zone air capacitance, this is the capacitance of the air inside the zone. Well, what if someone opens a window or opens a door of a zone? There's going to be sort of fresh air coming in. The volume still remains the same, but it may be more dense air or air with some different thermal properties that can come in. And it will change the zone air capacitance over time itself. So we are assuming in this model that the physics or the parameters, the thermal properties of the things we are modeling, the elements of the A, B matrices, which are these 1 over RC, and these are highly nonlinear in the parameter space. They are all time invariant. And so that is why this system is linear time invariant. So let me also make another point which will become very important next week. When I say the system is linear in the LTI, we mean it's linear in the state and the inputs. Okay, so the rate of change depends linearly on the state. It's not a function of T1 square or cosine of T1, and the same for the inputs. But it is not linear in parameters. Look at this term. HA over RC is highly nonlinear in H, R, and C. It's like a product and a division. So the model is nonlinear in parametric space, but it's a LTI model because it's linear in inputs and the state of the model. Okay, so I just want to make sure that's clear. So I said earlier that this is the state space dynamics, but we have looked at the state equations. But what's the other component of a state space model? You have x dot equals ax plus bu, but you also have another relationship, right? So you have the output relationship, which we haven't defined yet. And we've said this earlier, that the state equation is always this LTI dynamical model, but the output equation is always algebraic. It's not a differential equation. So if I say that I want to use the state of the zone temperature, so this term right here, as the output of the model, I can actually write the output algebraic equation that y of t, which is now just the zone temperature, is C times x. So this will give us the zone temperature plus d times the input. Okay, so this is just an algebraic equation because I need to define that. So questions on all of this, how we have taken the simple system and made a state space form. It's actually what you have done already in the previous assignment, but for a different system. So this is enough to have a very hypothetical case where you just have one wall and one zone, and we already know that real zones don't behave like that. So this is, the question really is that we have seen how to model an external wall, and the sort of subtext over there is that we consider this slab that we have modeled as external wall because the boundary condition outside of the slab is outside temperature and the influx from the sun, which are properties of external walls. But you could then ask, well, what about floors and ceilings and windows and other things, right? How do we model all these other surfaces that I went over this list of surfaces that we have to model to completely describe the dynamics of the zone? And intuitively as well, the temperature doesn't just depend upon what's happening on one wall. It depends upon what's happening on all the surfaces of the building envelope. So to do so, before we do so, I want to show you a mathematical or a programming trick that is very useful. So, let's say this is the 3R2C model of the external wall of this zone shown here. This is the exact same model that we've seen. So you have, outside temperature, which I've said TA for ambient temperature. You have TEO, so EO means external outside. EI means external inside temperature, because this is the external wall. You have the capacitors of the associated thermal mass of these states as CEO and CEI. They're usually the same, but they could be different. And then you have the zone temperature on the other side of the wall with convection between the internal surface and the zone temperature itself. You have the direct solar gain on the external node from the direct sunlight. And here we've also shown that on the inside surface of the zone, there is some radiative gain, which is coming from the occupants and the lighting, right? So there's both convective and radiative gain. We usually neglect radiative gain because its magnitude is very, very negligible compared to these other massive heat gains. So we already know this. The only difference in this picture and our previous picture is, instead of writing this resistance as R, I am using this term 1 over conductivity of the wall, right? So if you recall the 3R2C model, we had a term 1 over HA, and then there was this R, and then 1 over HA as well. So when we have that 1 over HA term, that's convection, but when you have a resistive term, that's conduction. And I'm just saying that the trick which will help simplify the mathematical expression of how we describe things is, we just define that conduction is the reciprocal of resistance always. And so if you make this notational change, you can write the same equations without any denominator terms. It's very useful when you program. You have to code this, and you'll build this model in MATLAB, and we'll estimate the R and C values from real data. That's what's lined up in this module. So a good practice is to think of even resistances in terms of 1 over conductivity. Okay, that's why we have made this notational change. Functionally, mathematically, everything is the same. So instead of having a term which says the T internal minus T external divided by R, I can just have a numerator term, and there's no denominators in this equation. So the other thing to note is that I'm making a distinction between the capacitances of the external outside wall and the inside surface of the wall, right? And in our simple 3R2C example, we both had the same capacitances, right? So we defined it, the thermal mass, if you remember, was density of this material times the volume of the material times the specific heat capacity of the material. And then we divided that by 2, and that was the C term in the 3R2C model. But that need not always be the case. We have seen that walls are layers, and so if you choose to prefer that I'm going to treat the first 2 layers as part of my external model of the wall, and the latter 2 layers as part of the internal surface of the wall, the wall, then you can assign them different thermal masses based on the materials of the layers. But the general rule is that the sum of the external capacitance plus internal capacitance is equal to the total capacitance of the thermal mass of the wall. So in simpler terms, in many cases, these two things are exactly the same, but they need not always be the same. Okay? And we will see examples of when they are not the same when you do the modeling. So let's go back to that question that we have seen how to model an external wall. How do we extend that to different surfaces, right? So how do we model ceilings or floors or other surfaces of the zone? So the big insight is that ceilings are also walls, okay, and floors are also walls. Everything is a wall, right? So if you like Pink Floyd, so everything checks out. So we don't do anything. We just use the same 3R 2C model, and now all we have to change is where are the direct heat gains going, what is the boundary condition. That's it. The structure of the model is exactly the same as the ceiling and the floor, which is why I promise you that I gave you a long list of different surfaces that we will model, but it will be very simple because everything is the same. Okay, so to model the ceiling of this hypothetical room, we look at the temperature or the boundary condition on the other side of the ceiling. Let's say this ceiling is the true roof of the building, right? So in the case of this lecture hall, the ceiling is actually maybe the floor temperature of the zone above us because we are in the basement. But let's say in this picture, you are truly located at the top of the building. So your outside condition would be, again, ambient temperature. And you, again, would receive direct solar gain because the roof was also exposed to direct sunlight. You will have the conductivity of the ceiling now, which is also layered in many cases. The inside surface of the ceiling will have its own state, the CI, and you can apply radiative gain from occupants and everything to the ceiling now. So literally, I have taken the external wall and rotated that 90 degrees to visually associate that with the ceiling. But the equations are also exactly the same. Okay, so the only thing you have to pay attention to, and I cannot emphasize this enough, is what is the boundary condition driving the 3R 2C, and where are these direct gains getting applied in your model. Okay? So just for the sake of argument, it's not shown here, if I had to model the floor using 3R 2C, what are some examples of the boundary condition that can drive the floor? So the floor is not subject to outside air temperature, so what could be the boundary condition, in your opinion? Like, what does common sense dictate? Very good, right? So in our case, since we are in the basement, we can look at the average ground temperature as the temperature which is driving the dynamics of the temperature of this lower surface of the floor. What is another example? If, say, we are not in the basement, but we are in the first floor of a building. What's the boundary condition then? The floor below, okay? And so in that case, you may not have a term which is just direct solar because it doesn't make sense. The floor is not getting exposed to direct solar radiation. So you use the same thing, but you're just changing the inputs and the boundary conditions to this 3R 2C. So this works for any surface. So we've covered, external walls, we've covered ceilings, we've covered floors. The same is also true for internal walls, right? So what's an internal wall? Which is not getting exposed to direct sort of, external boundary conditions. So technically speaking, even if you are in the first floor and there's a floor above you and then there's a floor below you, then your floor and ceilings are kind of internal walls because their boundary conditions are other zone temperatures. In this lecture hall, I think all our walls are internal walls. The ceiling is also an internal wall. The floor is the floor in the true sense. It's not like being driven by ambient temperature. So for an internal wall, you can actually do many things. You'll see an example of this shortly. Like in this room, we have 3 internal walls if we treat the ceiling as its separate branch. So you have the choice of having 3 different 3R 2C models, one for each wall. But if you think about it, and that applies to this room, the outside is just a corridor. And this left wall to my left and the wall at the back of this room, they are connected to the same corridor, correct? So there is a reason to assume that the boundary condition would be just the average corridor temperature. But this wall behind me is connected to another lecture hall, which is thermally conditioned. So maybe the temperature there is different from the corridor temperature. So if I had to model this very room, I may just aggregate all of these walls into one 3R2C branch and drive them with the corridor temperature. I may model this separately because of the temperature adjacent to me. Same goes for the right-hand wall. Same goes for the ceiling and the floor. So you can, as a designer, as a modeler, building automation expert, lump these things together when they make sense, physical sense. So really, you need a separate branch only if the boundary condition is significantly different from other surfaces. That's what it boils down to. So this applies to almost all surfaces. There are some exceptions to this rule. One of them is windows and doors, or in general, anything which is glass or not regular heavy thermal mass material. So the 3R2C model is useful when the surface or the boundary itself has some thermal inertia or some capacitance. But a window doesn't really hold that much heat in the panes of the window. It's very good at blocking heat and transmitting and things like that. So we can actually simplify things. So we can, even if you had, say, in this picture, 4 windows on the external surface, what you could do is you could simply look at the area, cross-sectional area of these 4 windows, their average thickness or individual thickness, or if they are the same, then they're the same thickness. And you just need a resistive term to model windows, right? So if this is my zone temperature and the temperature outside is TA, I'm just modeling the window as a single resistor because I claim that it's fine to ignore the thermal mass of a window. And you will see this when we look at Energy Plus next week. A window also has layers. It usually has some glass layer and then some air gap and then another glass layer. So you have double layer windows, and they come in all shapes and sizes and variety of glazing, anti-glazing, insulating. So the air gap is usually not even air, it's argon or some inert gas to provide insulation. But anyways, the point is that windows or likewise glass doors or even wooden doors, we can ignore their thermal mass because it's negligible compared to the mass of the surface they are installed on. Okay? So we are making all these hand-wavy high-level assumptions because we want to keep the model realistic. I mean, you could, and you will see that in Energy Plus, we don't do that. We don't make these assumptions. That's why this is a gray box model. We are doing physics-based modeling, but not white box way. White boxes, you model everything in its full detail. Gray boxes, you are making these assumptions of lumping things together, treating walls as if they're just one entity, and so on and so forth. So that's one exception. Glass surfaces, especially, I emphasize glass because that's what you have to do in your homework. And then another thing, which is like a callback to what I showed earlier and promised that the reason I'm showing this is because this is relevant to what we will model. In ceilings, it's not always the case that this is like a false ceiling of the zone. The true roof may be here, and this is getting subject to outside solar, outside temperature. But I've shown you this picture before where the point was that in some cases, there is not a dedicated ducting system to bring the air out of the zone, and that has a special name called a plenum. Many residential homes still use plenums. It's rare in commercial buildings. But if your boundary condition for your zone is a plenum, you can almost think of plenum as a different zone of its own. Right? It's like a subzone, and then there's the real zone. And so again, this false ceiling or this drop ceiling, which what I suspect what this is, it again may not have enough thermal mass to really change things. So we can simplify sometimes our ceiling if we know the plenum temperature, and you can just use a resistor for your ceiling branch instead of the entire 3R2C. So that's something again that you will have to do in your assignment. But you can always revisit this slide to make sure you understand what a plenum is and how it can be modeled, which is much simpler than a 3R2C ceiling model. So to recap, this is what we do. Okay? To create a RC model of a single zone to predict its zone temperature, we combine any exterior wall and treat it as a single wall. Right? So any exterior wall which is subject to the outside sort of air and outside solar, you can just treat that as a single branch in your 3R2C model, where you will estimate the values of the R and C based on the properties of the material of the wall. Windows and doors don't have thermal mass, so they can be just resistive elements. That's the second point. Ceilings and grounds are the same as any other wall, except that the appropriate boundary condition is applied. The same goes for internal walls or anything which is between two zones. It can be the same 3R2C, but the boundary condition is the other zone temperature. And then finally, the common inputs to this model are heat gains, both from outside and from inside, convective and radiative, and all boundary temperatures. These are sort of the characteristics of a RC model. So when you put everything together, this is what you can end up with. Okay, so on the very first day, actually, I showed you this picture, and this may have reoccurred when we went into HVAC operation, and it seemed like this is a mess, and what is going on. Now it's crystal clear, right? You have a branch 3R2C for external wall. You have a 3R2C branch for ceiling, 3R2C branch for the floor, 3R2C branch for internal wall. You have windows, which is just resistive. The zone has its own thermal volume of the air, and there are some direct heat gains into the zone. There are some direct heat gains wherever appropriate on the walls. So we don't care about the geometry of the zone. This picture tells me everything I need to know about how I'm going to model the zone. So this is your mathematical model. This model is exactly equivalent to the state equations that we have been spending so much time on. Is everybody convinced that these two things are the exact same things? And so just like we wrote a state space model when it was the simpler case of T1, T2, and T zone, just 3 states, you now have a lot more states. So your state space model is now, the A matrix is a big fat matrix multiplied by a long number of states. Questions on this? Okay, so again, I like to associate equations with these branches. So that external wall is this equation, right? So capacitance of external outside times the rate of change of temperature of external outside is the convective heat rate between ambient temperature and outside surface plus conductivity times the differential of the wall itself plus direct solar heat gain on the external surface, which is the same as this picture. Likewise, the ceiling is appearing there. So these are sort of the drivers, if you can think of, which are influencing the zone temperature, right? Zone temperature is sitting right in the middle of this network. So these different nodes of this network are different states. Not all nodes are the states. Some nodes are boundary conditions, like ambient temperature, but most of the nodes are states. So let me zoom into the center part of this picture and look at what's happening in the zone when we put everything together. And that's that picture on the top right. So, we've just cropped that image to look at what is happening to the zone temperature. And what is happening is the following. You have the thermal mass of the zone air times the rate of change of temperature of the zone is equal to this convective heat transfer between the external wall, the inside surface of the external wall, which is why it's EI, and that's why I encourage you to stick with this convention when you submit your homework as well. It's not required, but it's just easier to grade if it's in this format. And so you have this convective heat transfer with the zone plus convective heat transfer with the inside surface of the ceiling, which appears where? It appears here. This is supposed to be pink, but it's not showing properly. You have the internal wall, the combined sort of conductivity of all internal walls. So you can combine all internal walls if they are driven by the same external sort of boundary condition, which appears here, this term. So these are all 3 convection terms. Then you have, again, some convection with the floor. So the top surface of the floor, the temperature there is this, which you can call as the inside surface of the floor as a wall. So there's a convection transfer there. There's a heat transfer purely resistive through windows. So resistance of the conductivity of the window times the temperature difference across the window, plus there is direct heat gains to the zone itself, which are these HVAC gains and internal heat gains, convective heat gains. Okay, so together, when you put all these pieces together, you can describe the temperature evolution of a zone, which is what our goal was, using very simple principles of physics. And that's sort of the take-home message of the first module, how we can use physics to model things. I also want to make one more point, which I think I forgot to make when I showed you the floor. So when we are discussing the 3R2C model of the floor, we established that the boundary condition could be the ground temperature. But do you think that the heat transfer between the ground temperature and the outside surface of the floor, is it going to be convection or conduction? It will be conduction, unlike the other ceilings and external surfaces. So only when there is air which is on the other side of the surface, you can use the convective transfer. So be careful when you model the floor, the branch of the floor, just so that it's super clear, this resistor is not convection. This will be conduction, because this floor will conduct to some temperature of the outside surface. Okay, so we do all of this, and I will leave this as an exercise. This is really your homework. You will do this for a zone where you will take all these equations, understand them for the zone that I will give you, and then you will write the state space form. Okay, so this picture can be represented as a state space model, because really this picture is a bunch of ODEs. So to give you an example what that could look like, so what are the states of this model? All these external and internal temperatures that we are using to represent, right? We have made these modeling assumptions that this entire wall is one node temperature. So that's a state, and we have an ODE for that state. So anything which has an ODE is a state of the model. So we have almost 2 per branch, so external, ceiling, ground, and internal, and the zone itself for this picture. It can change for a different zone configuration. Then what are the inputs to this model? These are states, but what is the U vector for this entire model? It's a lot of things. Let me go over all of them at least once. Outside ambient temperature of the air, temperature of the ground, temperature of the internal zone on the other side of the internal wall, external solar flux on the outer surface of the wall or the ceiling, so that's E or C, radiative gain which is applied to the external wall, ceiling or ground, or well, we are not applying it to the internal walls. We have transmitted solar. So some solar is coming through the window, directly getting added to the zone. We have convective heat gain from the occupants, let's say, and appliances. And then HVAC can be treated as this term that I had once introduced, sensible gain, because it's directly influencing the temperature of the air. So we make a distinction between internal heat gains as being convective, or when it's from the HVAC, you can usually see in literature it's called QHVAC or Q sensible load or sensible gain. These are all boundary conditions and inputs to our state space model. And we have a bunch of parameters, which are the conductivities and the capacitances of this model. We can donate all of that by alpha. Right? So in the previous picture, I explicitly not only show what is changing with time, I also show that A, B, C, and D depend upon alpha, where alpha is the vector of all parameters of this RC network. And this is exactly what is unknown to us in a zone. Right? By looking at the geometry of the zone, we can draw this state space network, we can write the equations, but we actually need to know the thermal mass and the specific heat and the convection properties of materials to estimate these RC values or UC values. Right? So this is what is called gray box modeling. It's gray box because it's not as detailed as something you will see in the next lecture, which is energy plus, which is white box. So it's a very happy middle ground, which it uses physics and it does the job of being a useful model to predict the zone temperature without getting crazy by modeling the XY distribution or the 3D distribution of temperature. We don't really need to go into that detail. Why? Because our ultimate objective was to control for demand response, to ensure thermal comfort, right? The whole reason why we wanted to predict stuff was that we wanted to be able to control the set points of the HVAC to guide the temperature in a certain trajectory or a desired range so that the electricity consumption is temporarily reduced if we are talking about demand response, right? So again, to refresh and make connections to this whole idea of model-based control, which is what motivated us to create this model in the first place. When we look at the list of temperature inputs, it's this long vector. I want you to always think of inputs. They belong to two categories. One is what you can call as non-manipulated variables or disturbances. What does that mean? It means that many of these inputs are not in my control. I cannot manipulate them. I cannot change the temperature outside. I cannot change how bright the sun is today. I cannot change the radiative gain that you are emitting right now. Technically, we can, but for the most part, that's not what we change when we get a demand response request. So these are non-manipulated or disturbances to the model, but there are some things that we can directly change. Then those are control variables. Those are called manipulated variables or control variables. So in this long list of inputs, which is the control inputs, which ones do you think are control variables or can be described as control variables? The temperature, you mean this temperature? This is the temperature of the adjacent zone. Correct, right? So what are we controlling? We are controlling the thermostat. We are controlling mass flow rate, supply temperatures, all that stuff that, which was the introduction to HVAC. All of that is lumped in nothing but just this one term here. So in fact, everything in this model is non-manipulated. And we are directly controlling the sensible cooling rate or the HVAC cooling rate or heating rate. And once again, I like to throw in these conventional things which you will often find in literature when you read a paper tomorrow, which may not be buildings, but any paper, and it has some control vector. It's again sort of convention to stack the control variables at the end of your input. It's just convention. Also, you'll find a lot in the libraries of the control sort of state space modeling. That's also like a programming convention. Okay, so what we can control is actually Q-sense, and we've already seen what does it mean to control Q-sense. It means to control either the supply air temperature or the mass flow rate that you are sending into the zone. So there's something hand-wavy about this equation. Usually, I said that the load or heating or cooling load of a zone was mass flow rate times the specific heat of air and supply minus return or return minus supply. So here we are just assuming that return temperature is the same as the zone air, which is a reasonable assumption again. So now you can associate the sensible gain and you can actually dissect it into a combination of two things you can individually control, which is the mass flow rate and the supply air temperature. These are things you can control, will go into the zone and will, based on these disturbances, cancel them out, right? So mathematically now what you have seen, what it means when I used to jokingly say that HVAC is canceling this heat that humans are generating. This is what is happening all the time. We are regulating the mass flow rate and supply temperature to cancel out all those disturbances, which are indirect and direct heat flows into the zone air. So when we look at the zone air dynamics equation again, you just saw this and I broke it down into each individual component. This last term is technically this term. okay? Where the red variables are your control variables now. So if this was my model, if I actually use this entire expression instead of lumping everything together into sensible load or HVAC load, what will happen is that my inputs now would become this vector. So instead of Q sensible, I have two control inputs, mass flow rate and supply temperature set point. And the problem is, and you can visually see what the problem is, all of a sudden your model is no longer linear because you have two control inputs which are multiplying with each other. You have a product of supply air and T supply. So you have almost like a U square term in some sense, or U1 multiplied by U2 to be direct. So your model is no longer LTI. That's why we want to lump everything together into just one term, and you will see how later we can deal with that problem too. Okay, by doing so, the model has become nonlinear, or the correct term for this is bilinear. When two things multiply with each other which are different, they are bilinear. So let me again pause, and any questions whatsoever on how do you go from a hypothetical zone to a state space model, because that's your next assignment pretty much. Okay, any part of this which was not clear, too fast, too slow, just let me know. And these slides are, as you know, always available for your reference, so you don't really need to worry about remembering these forms of equations. If you understand 3R2C and the exceptions to 3R2C, you can model any zone now. Okay, so let me give you a real life example of this. Enough of thought experiments and hypothetical stuff. This is a sort of a CAD diagram of a real building. It's located in the Navy Yard in Philadelphia, where I went to grad school. And we actually modeled the entire building, but I'm going to describe just how we modeled one specific zone of this building in reality. Right, so this zone was, I believe, on the second floor or on the first floor of that building, the zone shown in color. And it's a pretty large office space, many cubicles, about 60 to 70 occupants during peak occupancy hours. So there were a lot of choices we had to make, right? So like if you look closely, the zone is here, but there's like a lobby or a porch area just adjacent to the zone, or almost like a corridor like we have. And then there's other zones all around. And there's a zone above and a zone below as well. So we had to make a lot of modeling choices, like, does every internal wall require its own branch? That's a very common modeling choice in the RC network. And I've already answered this for you. The answer will depend that for each of the internal walls, is the boundary condition on the other side very different from each other? If so, then yes, it's a good idea to model them separately. If they are more or less the same, you can combine all internal walls into a one hypothetical internal wall in your model, and the boundary condition could be either the maximum temperature or the average of all these three individual temperatures. So these are sort of modeling decisions you will make when you make the model. So what about windows, right? There were, I think, about 8 windows or maybe even more windows on the on this external facade of the building, so this wall over here. And as I've told you before, what happened was that all windows happened to be exactly the same dimension, same material, same cross-sectional area. So my model just ended up having one resistance to represent all of the windows, not 8 different resistances, right? So it's a aggregation game. The model doesn't care whether you model each window with R1, R2, R3, R8, or collectively estimate the resistance, assuming that the window is the sum of the all 8 cross-sectional area. Right? The resistance of the window depends upon the thickness and the cross-section area. So I can just add all the 8 cross-sectional areas, assume the same thickness, and just represent it by one window, functionally. Do doors have thermal mass? In this case, no, they did not, because they were glass doors. So we modeled them as windows. And how did we compute the heat gain at any time, which is really, you have to do this because that's what drives the surface dynamics and the zone dynamics. We had to model a lot of different heat gains. So we had to measure and model solar irradiance. I will show you in a bit how to do that. We had to measure the solar incoming through the windows itself, both convective and radiative heat gain. HVAC was fully instrumented, so we could measure everything, and we had boundary temperatures for all the walls and surfaces of the zone. So you may wonder where does this values for how much heat does an average human emit, where does it come from, or how do you figure that out? Do you use the same value for all occupants, or what's a systematic way to estimate this convective heat gain from occupants or from humans? And so a lot of people over a lot of years have done excellent work, very, very detailed work. There's a whole body of, just like you have IEEE or body of engineers, there's a body called ASHRAE, which let me recall what it stands for. I think it's the American Society of Heating and Refrigeration Engineers, ASHRAE, okay? So what they have done is they have collected real data, real measurements, and created models where if you input the metabolic rate of a person and the sort of the body temperature or the air temperature, sorry, not the body temperature, it will give you the total sensible heat gain emitting from that person. So we will not use this model. So the Energy Plus tool that you will see next week actually uses this equation. For our purposes, we are happy with some sort of a lookup table. Okay, so essentially, if you are seated at rest, which we all are right now, unfortunately, this is not a theater or a movie, but this is what we are doing. So each of you is like a 100-watt bulb right now, okay, according to ASHRAE. And so based on the activity, you can just pick some watt per meter square or watt per occupant, and that becomes your internal gain. Not only that, you can break it into internal gain, which is convective and radiative, or sensible and latent, because we have both components. Okay, so visually what we do is we look at the zone air, the volume of the zone air, because that will give us the capacity or the thermal mass of the zone. Then we look at each of the surface. So external surfaces have outside irradiance and ambient air driving the boundary condition. There's conduction, and then there is convection between the inside surface and the zone air. Then you have internal heat gains, and they are responsible for both convective and radiative gain. And remember how radiative gains were applied to the inner surfaces of the zone. So the electromagnetic emission from my body is getting absorbed by every single piece of furniture in the zone, and then that is emitting, and there's a convective heat transfer between that surface and the zone air temperature. So you can break down your heat gains into convective and radiative as well. You may have some direct radiative gains or irradiance from the windows from solar as well, which is heating up the furniture. But at the end of the day, if you look closely, the only thing changing the zone temperature is sort of convective or direct cooling load. Okay, and that is consistent with our view of the equation that we just saw in the zone temperature. Either there was a convection term with the inner surface, or sort of a direct cooling load or a heating gain term. So going back to this question, how do you compute the total internal gain? You have these lookup tables and references that we use. We are not really at this stage concerned with modeling that metabolism and whatnot. So this is what I said earlier, right? So does anyone know how do you measure direct solar irradiance? What can you use to measure the solar flux on a building? Do you know what kind of sensor do you need for that? What is solar flux? It's like just electromagnetic waves. So, luminance sensor has the correct principle, but it's only sensitive to the visual range. So you need something which is similar to, or let me repose a question. What type of sensor is a luminance sensor? What actual sensing element does it use? It's a very simple element, actually. So you just have materials whose resistances change based on a particular spectrum of light. So in a lux sensor, it's called a LDR, light-dependent resistor, or an array of light-dependent resistors. And based on the intensity level, the resistance will change. You can measure the change in resistance by looking at voltage and interpret that as some function of flux or luminance. The same thing happens for irradiance. It's a different part of the spectrum though. And the sensor is actually called a pyranometer. This looks like this UFO sort of sensor over there, but it has a dome to gather flux from all directions. And inside this are special sensitive LDRs, which are sensitive to this range of infrared and ultraviolet, rather than just visible light. Okay, so in fact, this is pretty expensive, but what you use this for is that you don't need a pyranometer on every surface. That would be the best case scenario. But in reality, what you do is you have a single site which is, say, upward facing or a horizontal plane, and it is measuring the flux at any given time on the horizontal plane. And then we can just use that value and compute what would be the flux on a wall which is south facing or east facing or at 30 degrees. So you don't need to measure the flux at every wall. If you can, then that's really good, but you typically don't. You just measure the global flux on a horizontal plane at any site, and then you can use modeling again to predict what a south-facing wall or an east-facing wall would be receiving at this point. So these are sort of our measurement errors in this picture of modeling errors, if you recall what I'm referring to. So this is how you measure flux. Other things are easy to measure. Temperature is very easy to measure. So if you go back, this ugly picture is the floor plan of the zone that I had to model for that building, right? So we were going to model this zone. This is the wall which had those 8 windows. This is that porch area, and there was an adjacent zone over here. Reason I wanted to show you this picture is because when we were talking about how do you model a building, the first step is you get this geometry or building information. And this is what it looks like. This is literally the scan of what we got when we had to model the building. There's no CAD model or anything. So this is again, causing a problem because we can't figure out what these different surfaces are, what are their properties or thickness. It's not even legible, right? So you can barely make out what these dimensions are, but you need this to model the zone correctly. So I wanted to just show you this is how the real world is. It's maybe not true for modern buildings which have very well calibrated computer models, but any older building, this is what you have to work with if you want to really do this in the real world. So how did we model this? Here's the equivalent RC model for not just one zone, but this entire block. Okay, so let me sort of orient you a little bit about what is going on. So let's look at this zone, right? This is zone 8, which is up top here. So zone 8, you have an external wall, and this should be familiar. This is nothing but a 3R2C external wall model, this top branch, where the boundary condition is outside temperature. So it's actually a sum of this wall, and all of this. All of this is external wall, modeled as a single branch. Then you have ceiling, which is the boundary condition is the temperature of the floor above. You have the ground for zone 8, where the boundary condition is the ceiling of the floor below. And looks like, this is the windows in zone 8, this branch over here. And then it has interactions with other zones, which are these other 2 branches. And this is the zone which I had colored before, and it has the same 3R2C model. I won't go into each and every detail at this point. And you can explicitly then say, I want to model the interaction between zone 2 and zone 3. So that interaction is taking place here through this surface. And then 3 is also interacting with 8, 2 is also interacting with 8. But it may look, again, unnecessarily complicated. It's not. It's the same 3R2C applied to whatever configuration. We are agnostic to the real configuration of the building, because all that dictates is, to some extent, what nodes are connected to what, but for the most part, the geometry of the building just tells us the values of the RC parameters of this model. So this may look very messy, and so there's another representation that I want to show you that you may find in literature. So this is a RC network. Sometimes what people do is instead of having a network where the zone temperature is a single node in the middle of the network, just for simplicity and to make it less crowded, Because if you have too many surfaces, there'll be many RC branches, so it doesn't appear good, or you can't make out what is going on. It is unnecessarily sort of complicated over there and crowded. So people often they just use this idea that let me not represent zone with a single node, but like a line, a voltage line, and just connect everything to this voltage line. It's just the same thing. It's just visually more easier, or some people find it easier. And yeah, so you can find the same model that I showed you before drawn in this other format. So it's more legible, if you will. It's your choice. I have to just tell you that you don't get confused if you see a solution set which has T-zone as a line. You now know what that means. Okay, so now in the last 5 minutes, let me tell you what you have to do for your next assignment. So your assignment is due 1 week from now, next Thursday. It's already on Colab and on the course webpage. If you haven't already seen, all the assignments for the course are already posted till, I think, the beginning of the automotive module, more or less. So, by all means, feel free to jump ahead, if you will, at your own time to see what is coming. But let me give you an overview of what remains to be done in the first module in terms of assignments. So this is the zone that we will model. Okay, so this is the geometry or a visualization or rendering of the zone. It has 4 perimeter zones. Perimeter zones are, these 4 external zones. They are called perimeter because they're on the perimeter of this building. And then there's an internal zone. And so for your assignment, we will not model the entire building. We will even begin with like a very simple example to only model one zone of this building, right? So we'll model this space 3 is the name of this zone of the building. And so then, your assignment 2, which is you can grab a hard copy after the lecture today, you have to create the RC model structure for this zone based on its walls and ceilings and windows and blah, blah, blah. In the next assignment, we will actually start looking at the values of the RC parameters of this network that you build, and you will finally end up with tuning the values of those parameters from real data from this building. Okay, so that's sort of the direction of the weeks to come in this first module. I think we have maybe roughly 4 or 5 lectures left to cover all of this. So in assignment 2, you are given this zone. This is the top-down view, and you only have to model this space 3-1, which is this one of the perimeter zones. And the assignment goes into a lot of detail. Let me quickly sort of present a summary of what you are expected to do here. So this space 3-1, that's the name of the zone. It has the following inputs. I've already given the list of inputs, right? So all of them should be familiar by now. So we have ground temperature, outside air temperature. This should ring a bell. We have a plenum in this zone. Okay, so I'm not going to explain again what that is. Then we have external heat gain, internal heat gain, cooling load. We are ignoring any radiative gain to simplify things, right? So don't have to worry about radiative gains at all. So all 3 are pretty self-explanatory. We have neighboring zone temperatures, right? So if you look at this zone, it neighbors 4-1, 5-1, and 2-1. So we have 3 neighbors and their associated zone temperatures. And then you have the zone temperature of the space you are modeling itself as an input as well, or as a state. Depends upon how you want to use it. Okay, so you have these inputs, then you will build this RC network. This is not the solution, so even if you go and visit this slide, don't just submit this. It's incorrect for that zone. So you have to actually spend some cognitive load over there to figure out what's the correct RC network. But you will get something like this, and you will tell me the physical interpretation of each of the parameters of whatever you have modeled. Okay, so you don't have to really estimate their values. In fact, the assignment doesn't have enough information for you to do that. All you have to do is build the RC structure, tell me what are the states, what are the inputs, what's the model order, is this LTI or not, many things that you should be knowing by this point. And you finally have to tell me what are the parameters, what is their physical sort of interpretation. You have to make design choices of figuring out whether you want to treat every internal wall differently or lump them together. If you do anything, you have to give like a justification for that. So this is a purely pen and paper. This assignment has no programming parts. But that doesn't mean you just have to turn in pen and paper. If you want to turn in some LaTeX tool or some PDF, you are more than happy, invited to do that. And in fact, if you're wondering, how do we build these kind of things, you can search for a tool called, well, you can do this in many tools. CAD can do this easily, any CAD tool, but Microsoft has this tool called Visio, which has like a library of elements which are resistors and capacitors, and you can create such diagrams. Or I'm pretty sure if you Google or spend 10 minutes figuring it out, there's also someone who has created a PowerPoint library with all these elements. So you can actually piece this together in PowerPoint as well if you want to spend that much time. So this is your assignment. It's due before the lecture next week because this assignment really is what we have covered today and the lecture before. So you have all the information needed to attempt this and do this successfully. So next week we will do two things. In the next lecture, I will show you an example. Like I told you on the first day that in every module, I will also show you example of a tool which domain experts use in that module. So time and again, you have heard me saying this term called energy plus. But in the next lecture, I will walk you through what energy plus is, and it's a white box model. So it does pretty much what we have done for the gray box, but in more insane detail, right? So everything is much, much more detailed in energy plus. I will give you, it's not possible to learn energy plus in a day, and that's not expected of you. It has a very steep learning curve, actually. It takes years for people to know the entire software. But it will become clear what the difference between white and gray box is after you have seen energy plus. Then you will really appreciate RC models, because right now RC models seem like it's easy / lot of work. Once you see energy plus, you will say, oh, it's a no-brainer that we should build RC models. So that's the whole point of the next lecture. I will send an announcement again. If you want, you can install Energy Plus to follow along what I do in the next lecture, but it's not again required. So you can just listen in and you will take away the key messages. So that's it for today. Grab an assignment and let me know if you have any questions.